Okay, so let's take a look at this function here. We're going to analyze it and sketch a graph. So we're going to go through all the things that we just talked about and find out what they are and then try and put them into a graph. So I'm going to either refer to this function as y or as f of x, depending on what I want to use at the moment. Okay, so the first thing is, let's talk about domain. All right, if we take a look at this function here, obviously rational function, so we'd have to look at the denominator, but x squared plus 3 is never going to be 0, so our domain is actually all real numbers. So that's just good to know. All right, so then I'm going to go to intercepts. And let's start with the x-intercepts. So I'm going to set y equal to 0. So I'm going to say x squared over x squared plus 3 is equal to 0. And that's going to tell me, so that the only way that that is 0 is if x squared is 0, and the only way that is x equals 0. And so that's the x-intercept. That would give me the point 0, 0 on the graph because I just found x was 0, and I did that by setting y equal to 0. All right, the y-intercept, then I'm just going to set x equals 0. So I get y is 0 over 0 plus 3 is 0. So I get y equals 0. Then that obviously gives me the same point because I found y equals 0, but I found that that happened when x equals 0. So if you have 0, 0 on the graph, it's both an x and y intercept. But that's okay. So basically at this point we know 0, 0, the origin is on the graph. Okay, next, asymptotes. Okay, so let's think vertical. All right, so remember our function, let me just write it over here so we can see it, is y equals x squared over x squared plus 3. We'd be looking in the denominator to see when it's 0 and the numerator is not 0. But again, we just said that that's never going to be 0, so there are none. Okay, horizontal. That's where we'd want to take the limit as x approaches infinity and the limit as x approaches negative infinity of this function. So x squared over x squared plus 3. Now often those will be the same, but I like to do them separately in case they are different, which can certainly happen. So this is not a difficult limit. Remember, this is when you're taking x to infinity and you've got a polynomial over a polynomial, a rational function. You just look and compare the powers. So I've got x squared over x squared. So I'm really just looking at the ratio of the coefficients. So that would be 1. And the same thing here, that's not going to change if I go to negative infinity. And so what this tells me is I do have a horizontal asymptote at y equals 1. Okay. So now we want to start talking about extrema. So that's going to involve the first derivative. So again, let me just put our function here again so I don't have to go up and look at it. All right, that's the function. So if I want to take my first derivative, this is a quotient rule situation. So derivative of the top, 2x, times the bottom, x squared plus 3, minus the top, x squared, derivative of the bottom, 2x, all over the bottom, squared. Okay, and so I have to work this out now. So that's going to be 2x cubed plus 6x minus 2x cubed over x squared plus 3 squared. All right, and that's going to end up being, we're going to get the 2x cubes canceling, so we're going to get 6x over x squared plus 3 squared. Okay, so there's my first derivative. Let me bring this down here. So f prime of x is 6x over x squared plus 3 squared. All right, and that I'm going to want to find critical points, so I have to ask when is that 0 and when is that undefined when the original function is defined. So when is it 0? Well, just look at the numerator. 6x would have to be 0. X equals 0. It's not undefined anywhere. Okay, so on to a chart, first derivative chart. And the only point I have to put, there are no discontinuities, and the only critical number is 0. So then, again, I go back to my first derivative here. I'm going to plug in numbers. So if I plug in, say, -1 for this region below 0, well, the denominator is always going to be positive, so it really just matters what the numerator is. If I plug in a negative there, it's going to be negative, and if I plug in a positive there, it's going to be positive. So I can see that, remember, this is the first derivative, so the first derivative being negative tells me f is decreasing, and the first derivative being positive tells me f is increasing. That also tells me that what I have here is I have the function decreasing before and increasing after, so I have a relative min at 0 something. Now, to get that y value, I would plug it back into the function. I've already done that before because we know that 0 was 0, 0. Okay, so I know some areas of increase and decrease, and I know the relative minimum. There is one, there's no relative maximum. All right, so that's good. So now I can go on to the inflection points. All right, for that, I will need the second derivative. Okay, so we do have this first derivative up there as 6x over x squared plus 3 squared. So the derivative at the top is just 6 times the bottom, x squared plus 3 squared, minus the top, 6x, times the derivative of the bottom, which would be 2 x squared plus 3 now to the 1 times 2x from the chain rule, all over now the bottom squared, so that would be x squared plus 3 squared becomes 4th. All right, so I have to clean this up a little bit. So what I could really do is I can factor out a 6x squared plus 3 squared from the numerator, because that will give me just not a square, just one of them, x squared plus 3, because that'll give me an x squared plus 3 left over in the first term, and then in the second term that would give me, the 6 is gone, I still have an x and a 2 and another 2x. So I have a 4x squared, a minus 4x squared there, all over x squared plus 3 to the 4th. Now one thing I can see is one of these x squared plus 3's cancels down there. So in the denominator I'll get x squared plus 3 cubed. And then I would have a 6 times x squared, so minus, so well, 3 minus 3x squared. I could do a little better than that. 6, no, let's take out a 3 so that we get 18. 1 minus x squared over x squared plus 3 all squared, or 18, 1 minus x, 1 plus x over x squared plus 3 cubed, I'm sorry, it was cubed. Okay, so that's a good form of our derivative there, our second derivative. And again, we'd want to know, when is our second derivative equal to 0? When is our second derivative undefined? When our original one is defined, original function. The second derivative is obviously, if I look at the numerator in this, at x equals 1 and negative 1, and it's not undefined anywhere. So if I go to my chart now for my second derivative, make sure we can see it. All right, so I'm going to be putting negative 1 and 1 on this. And then I'm going to be plugging in values into my second derivative here. So the 18 is not going to affect anything. The x squared plus 3 cubed, even though it's cubed now, the x squared plus 3 is always positive. So I really just have to look at what happens to 1 minus x, 1 plus x. Okay, so I am going to finish this in the next episode here, so stay tuned.